Okay, let's get started. Traditionally, for most of the time I've been here, local speakers didn't get introductions, but I was told that under the new regime they get introductions, so you have to suffer through my introduction. So our speaker today is our own Elias. He got his bachelor's degree in physics from the University of Göttingen in 2013, and then did part 3 in physics at the University of Cambridge in 2014. Then he returned to Germany to the Johann Wolfgang Goethe Universität in Frankfurt am Main. If you haven't heard of it, you probably know where it is. It's where the Stern-Gerlach did the Stern-Gerlach experiment. In 2020, he received his PhD there, working with Luciano Rezzola, and his thesis title was Probing Dense Matter with Binary Neutron Star Mergers. So you notice it's not so different from what he's talking about today. Then he moved to the Institute for Advanced Study in Princeton, where he was until last year when he joined our faculty. So 90 years ago, in 1934, Richard Chase Coleman, working in this building, derived the general form of the spherically symmetric static metric in general relativity. And in 1939, Coleman showed that any physical equation of state would lead to a maximum stable mass. And later that year, Coleman's tenants, Robert Oppenheimer and George Volkoff, used those equations to compute models of neutron stars using the equation of state of free neutrons. And they found a maximum mass for neutron stars of 0.7 solar masses and a radius of 9.5 kilometers. The 9.5 kilometers is still about right. 0.7 was a bit low. And our understanding of the strong interactions has improved a lot since then. And accurate models of rotating neutron stars require more complicated metrics than the static spherically symmetric one. And those were the subject of Elias's early work on the maximum mass of differentially rotating neutron stars. But following LIGO's discovery of GW 170817, he graduated from simulating 1 neutron star to 2 neutron stars.
Got promoted.
Yeah. And of course, doing 2 is much more complicated than doing 1. They're very time dependent, for example. And he also decided to make things more complicated by including magnetic fields and increasingly realistic neutron star matter. And today he will tell us about this work on neutron star mergers, frontiers, and computational relativistic astrophysics. Now, about the computational side, I should point out that for this past year, Elias was awarded 9,365,504 core hours on the NSF Advanced Cyberstructure Coordination Ecosystems Services and Support, otherwise known as Access. And I look forward to hear how he will spend those last 4 very significant core hours.
All right. Thank you very much, sir, for the great introductions. Thanks, everybody, for coming. I want to tell you indeed a little bit about what happens when 2 of the most exotic objects in the universe collide. In particular, if you have very exotic states of matter, what kind of transients can they power, how can we observe them, and what are the challenges that we face in their modeling, and why do we need computers in the first place. And so one thing that, of course, I have to mention first is the great success, I think, for underlying this work has been in numerical relativity and also in the detection of gravitational waves from merging black holes. We've seen more than 100 right now in the current observing run. Even more have already come in. One of the great successes done here by the SXS collaboration is very accurate modeling of what happens when 2 black holes collide. As I will tell you during the talk, the interesting thing here is because all the physics is known, at least if you believe that Einstein is correct for all practical purposes, is really a technical challenge how to make these pretty looking pictures. But what happens when you replace the black hole with its little sister, the neutron star, you'll actually find under those conditions, the physics is much more extreme, is much more unknown, and we have to do much more, have to overcome much more challenges, both in the physical modeling and the numerical modeling and in the predictions that we make. And this is really one of the frontiers I want to tell you today. So this talk will basically revolve around what's in the neutron star. There will be an initial part of dense nuclear matter, which is something that's very exciting, especially with current and future detections. What can we learn about those very extreme states of matter? A little bit about gravitational waves, and then mostly, well, one of the frontiers is there's a lot of observation that have come in, both on gamma ray bursts, on radio bursts, on associated kilonova afterglows. Many of those actually observed over in the astronomy department. And the question is, can we provide numerical models both to guide what they should be looking for and to interpret what they have already seen? And so this is really what this talk is about. And in telling you first what a neutron star is, I will adopt a different approach. If this was an astronomy colloquium, I'd tell you about the history of stellar formation, how they form in massive star collapse. This is a physics colloquium. I thought I'd do the Sesame Street approach. I tell you the why, what, and how. And so if you ask what a neutron star is, this is where we are in Pasadena. The first thing you could ask is, where do you place this thing? Is it something you just put in a basement lab? Is it something you put in your office, a parking lot, or a different space? Actually, it's quite challenging to fit the thing anywhere because that's roughly the size. It has a radius of about 8 miles, which would span all the way up here to Glendale and further north. And when you put it there, it's like, okay, great, you put this big yellow blob of space goo. There's some nuclear matter in there, as the name would suggest. But what does it actually mean in practice? What would the thing look like if we stand there? Well, if you ask, what are the other properties of the star? Well, it weighs about as much as the sun, 2 times 10 to the 30 kilograms. It's a very, very extreme limit. Now, as Sterl said, we know it's about up to 2.3, 2.4 maybe. And so does that mean if we sit here, if we go outside, do we just get sunburned? Is it just that, this is what we're looking at? Actually, not quite. A very interesting question I've been looking into with people over at Lind Environmental Sciences is, if you think that neutron stars have thin atmospheres of hydrogen, so they form little oceans, what would they actually look like? And you can simulate this. You can use the same tools people use to model atmospheres of Jupiter or exoplanet atmospheres. You can run a simulation, and you can ask, if you have a neutron star that rotates very, very rapidly, what would the pattern look like? And this is what you would see. So you'd see little hurricanes forming at the pole. There's definitely dependence on Coriolis force, because you see the hurricanes, you see the jet stream in the equator. And I think there's really an interesting way of applying technologies from different fields and computational tools to make interesting predictions. So this is what we would see. I think standing there would still be very unhealthy because we would have very strong X-ray radiation, notwithstanding even the strong gravitational redshift we've been. But either case, I think this is a cool thing. So what about the elephant in the room? Why is the thing called a neutron star? What does this have to do with nuclear matter? Well, if you take the mass of the sun, you put it into this tiny space, 2 times 10 to the 30 kilograms, 8 miles in radius, that's what you end up with. You end up with densities at the core of neutron stars, just even if you compute the average density, that exceed nuclear densities, meaning you'll get interesting phases of matter in the interior, which you might not find anywhere else other than in collider experiments. For example, you find that in the center of the star, you could get deconfinement of quarks, you could get color flavor locked states, if you've ever heard of that. Or in practice, if you think in kind of little cuddly toys, you get basically this little 3-eyed friend over there, the strange quark. Strangeness does not exist in regular matter, but it can be produced under the conditions in there. And one of the questions that we will be asking during the first part of this talk is, can we actually use gravitational wave for astronomical observations in order to put any constraints on the theory of the strong interaction, which in part actually was worked out here many, many years ago. Okay, and so for all practical purposes, you're like, okay, this is all complicated. Just think of the neutron star as being some onion. As you peel away the outer layers, it doesn't necessarily make you cry, but there's interesting nuclear matter inside that you want to learn about. Okay, there's one more thing I have to tell you, because so far I told you what the thing looks like, what it's potentially good for, big blob of space goo, things you can learn about strong interaction. But then what actually makes it important for relativity? Why do we talk about gravitational waves? Well, for this, we can compute a number. It's called compactness, but think about it more as the Einstein-ness of this object, because what I can do is I can just slot a mass in here. And then when you look at this expression, it looks like mc squared, famous formula, rest mass energy density. And this is compared to basically its self-bound gravitational energy, gm squared over r. Okay, so if this number is large, so if gravitational energy is comparable to rest mass energy density, then you really need general relativity. If this number is small, maybe you can still do it, it's cool, but it might not really be needed. So if you want to compute example numbers for this, for objects that we all love and cherish, like our Earth, the number is about 10 to the minus 11. It's still important if you want to do GPS tracking, because you have to very accurately measure time delays. But otherwise, for all practical purposes, Newtonian mechanics is a good way. If you look at the sun, the same number here is 10 to the minus 6. So it's still quite small, but a little bit larger. And then if you look for the black hole, the most relativistic object we can think of, if you just want to set the reference scale, that number is 0.5 if you don't have any rotation. Okay, so really, if you get close to this number, GR is very important. We can calculate that for a wide range of nuclear matter models, 0.07 to 0.3. Really, neutron stars are black holes' little sister in this. So they almost have the same compactness, meaning if you put that amount of mass into that amount of tiny space and you move them around with a time-changing quadrupole, you're going to emit gravitational waves. So this is a really important factor for that as well. And just to put that into comparison again, if this was the neutron star and this is where we are, it's really, really tiny. So it's a very, very extreme object. And if we can access it using macroscopic observations in the sky, we can really learn something about the interesting properties. So how does that work? Well, here's an example for the binary pulsar. If the two neutron stars orbit around, they emit gravitational waves. You can see this here in the background. This system won't merge anytime soon, so it's not interesting for gravitational waves. Actually very interesting because neutron stars have built-in walkie-talkies. They can emit radio signals. This is the cones that you see there. Whenever they cross our line of sight, it's a radio signal that you can see. It's one of the most accurate clocks because of that amount of mass is spinning around. It's very hard to slow it down. So really you get very, very good timing measurements from that. And the question then is really, okay, what happens now for the purposes of this talk? If we fast forward in time, if they come very, very close and they begin to collide. And as Sterl already alluded in the introduction, this is something where you really need computational tools because not just Einstein's theory is complicated, but in general, you cannot make any symmetry assumptions. When you really have the highly dynamical merger and whatever comes afterwards, it's some system where really you have to solve the full theory without any symmetry assumptions, any simplifying tricks, and then you can only put it on a computer, you can brute force it. And here we can leverage all of the advances being made in numerical relativity for the black hole case, as well as, and this will turn out to be very important for any electromagnetic signal, all the multi-physics advances done in other fields as well. So if you combine the two together, you can really do a holistic model. One thing that I want to point out is, Sterl said we have about 10 million core hours to do this. Actually, there's a big change going on in the community right now because this is the traditional system. This is where your CPU cores are. But things are very rapidly changing with the advent of exascale. Machines no longer look like this. They now look like these two, where we recently got access. And the effective number you get there is almost an order of magnitude larger. So we now have access to about 100 million effective core hours on GPUs. And so what's really interesting on this exascale computing side is that these systems are so powerful that you can solve problems that used to take you weeks or month in a time scale of days to maybe 1 week or so, which is really, really exciting. We can push to much higher resolutions, much more fiducial models. At the end of this talk, I will show you one example that's critically enabled by using this new technology. So it's very, very exciting in terms of what capabilities are coming up. The other thing that we want to do is we want to kind of think about what's the physics that goes into this. So what actually do we have to tell the computer to solve in terms of equations? This might be the most equation heavy slide that I will show in this talk. Okay. And so one thing we've already seen is general relativity. We have to think about solving Einstein. This is for getting gravitational waves. It's at some point the two neutron stars, after they've collided, they could form a black hole. So really gravity is dynamical. We have to account for this. And so that's the equation we have to solve. But because we have neutron stars, we also need to model the flow of the star itself. We need to do something just like the flow of water. So we solve it using a collective approach, hydrodynamics. I'll tell you a bit later on what happens if that breaks down, if you want to do a little bit better than this. But for now, let's say most models I will show you are hydrodynamical in nature. And then you want to add on additional physics that we've already heard about. Physics either coming because neutron stars have nuclear composition, so we have to really account for nuclear physics, or because there's strong magnetic fields. This will really determine many of the properties of the system, including all of the electromagnetic counterparts, as well as weak interactions. That's an interesting thing. This is like putting chemistry in the star, because neutrons can convert into protons and vice versa, and that will determine the kind of colors that you can see with your telescope when you look at the system, as well as other properties. So we have to put everything together, and if you wonder what kind of forces those are really all of the strong forces of nature at play in the dynamical regime. So it's a really cool system to test out all of those cool physics. Now, without further ado, if you put all of this on a computer and you solve it, this is what happens. This is showing you the last 50 milliseconds of the lifetime of a neutron star binary. The two neutron stars orbit. You can't see the gravitational wave emission, but what you can glimpse at is that as the two stars getting closer together, angular momentum is carried out. Eventually, the stars begin to touch and merge, so they collide very violently. Now it's just smashing two things together. All of the debris is flying out. Now it's leaving the screen. It's very neutron rich. Ultimately, this will undergo our process nucleosynthesis. It will produce heavy elements, and the heat produced in this process will power infrared and optical transients. At the center, you have a very hot, rapidly rotating phase of quark matter going around. This is very interesting for future detectors of post-merger gravitational waves. And then ultimately, what you form at the center is a black hole disk system. If we put more physics in, we run this for longer, interesting things will happen, as I will show you. So in order to summarize a little bit of what's going on, what I will do now is I will take the various stages of this movie I will go through them and I will tell you what's happening, what are the available properties of the system, and how can we relate them to the underlying physics, or how can we relate them to observations. And so the thing that has been very successful here, that has been done in 2017 by the LIGO-Virgo collaboration, was the first detection of gravitational waves from inspiring neutron stars. It's a big success, GW 170817. It's one of two neutron star mergers. There were also some neutron star black hole mergers, which I will not talk much about today, but if you have questions, happy to say something in terms of their modeling. And the cool thing there was that the gravitational wave signal coming from merging neutron stars contains interesting information. Compared to black holes, neutron stars are rather rare in terms of at least of what we have seen. Nature isn't really kind to us right now. You can basically see this is sort of the stellar graveyard of merging system. This was, I think, right before 04. So you have about 100 merging black holes at the top. You have a few neutron stars at the bottom. These are the orange points that I'm interested in. And then you have some of them where you collide a neutron star with a black hole. Those can potentially also be interesting depending on what the effective population is, if you really care about electromagnetic counterpart observation. Basically depends on if the black hole is very greedy, eats the entire neutron star, or if some of the neutron-rich matter is left behind after the collision. Okay, and what makes neutron stars interesting in this respect is that different from black holes, neutron stars are squishy, really like big yellow blobs of squishy space goo. Just like in a tidally interacting system here for the Earth-Moon system, if you watch the phenomenon of high and low tides at the seashore, the same thing happens in this system as well. Tides are interacting, the neutron star is effectively slightly squished, and the squishiness drains energy from the orbit. In other words, they just collide quicker. And that's something that has been very successfully been seen and has been kind of translated into constraints in the underlying nuclear physics properties. Something I've looked into, something actually people working here, including Katerina, have looked into much more in greater detail. And by now, I think there are really nice joint constraints between different astronomical observations from X-rays coming from neutron stars, as well as observations from gravitational waves that can pinpoint how big can a neutron star actually be. And you also have indirect constraints for how massive it can be. And so moving forward, if you actually extrapolate to the future, if we had better detectors, especially next generation detectors in, let's say, a decade or so, you would actually be able to constrain the squishiness, which is shown here in the x-axis with this delta lambda, to much, much higher precision, meaning that we can use many gravitational wave events that will come in then from merging neutron stars to very accurately constrain the equation of state. One thing that I find very curious there, and I thought I'd show this, is this will work except if nature really hates us. If it does so, there are a few models, because what the gravitational wave detector sees is not how big a neutron star is, it sees how squishy it is. And squishiness turns out to be degenerate. And so there's a very particular family of equations of state that Karen Rather and I, who's now a postdoc at IS and soon to be a faculty at Swarthmore, discovered, which we dubbed tidal deformability doppelgangers. Those have the property, just like this double of Barack Obama here. If you look from afar, they almost look the same. If you look very close, they may be different. And there are specific nuclear models that will evade what a gravitational wave detector can actually distinguish. But those are very rare, and I hope we will not have to deal with them moving forward. Another very exciting thing that I think will be really cool in this age, or will also be really cool if we connect it to cosmic collision experiments, is actually what happens during the collision itself. If you start out with very dense nuclear matter, you collide them together, you get hot temperatures in excess of 60, 70 MeVs, really conditions you probe in a collider. Nuclear density is 70, up to 7 times saturation sometimes. And so really you could ask, well, is this scenario in some sense akin to what a colliding experiment on Earth would do? And if you think, well, maybe this is a bit far-fetched, actually, there is one experiment that has been done in Germany, close to where I went to grad school, where they looked at low energy heavy ion collisions of shooting gold ions into a gold foil. If you look at this very closely, they find there's an excess in electron-positron pairs that you produce in this collision that is very indicative of producing conditions just as in a neutron star merger. So even we may not have to wait for 1 decade to see nuclear matter under conditions in mergers, we may also get there on a second route due to ground-based experiments. And one thing that's being done there right now, this scenario is upgraded for the largest and most powerful heavy ion collider on Earth. And so one of the targets that this will do is actually look at what are the conditions if you have those gold-gold collisions at much higher sensitivity, can you learn something about dense matter? Because I'm very excitable, and I think some crazy questions should be asked. You can even say, well, if you can do a simulation, why can't you simulate both systems? Why can't you simulate a gold-gold collision and compare it directly to a neutron star collision? Don't be misled by the scales that I'm showing here. The right scale is on femtometer scales. The left scale is on kilometer scales. So really these images should be different by 18 orders of magnitude. But the nuclear conditions that you probe in both are almost the same. And we can even identify kind of what number do you have to dial in the ground-based collider to get conditions very similar to a neutron star merger. So we can even connect the two regimes using a simulation-based approach. Another thing that this will be really, really cool for, as you go from the inspiraling gravitational wave signal, so this long wave part here and the gravitational wave strain, it's just neutron stars orbiting around, to a scale where they have collided. They're much more compact now. This is wobbling around remnant. This will continue to have an extended ring down signal, and this ring down signal imprints very crucial features of the underlying microphysics. And if we have advances in detector technology, such as those pushed by Lee and Rana, maybe we'll be able to actually learn something from the data that will be coming in. Things that we have to care about is exotic degrees of freedom. Can we actually get our three-eyed friend, the strange quark? How would that look like? Is this something we could potentially see in data? And if so, what would it do? What about finite temperature and composition effects? Does it actually matter how many neutrons I have compared to protons? Or does it matter how much pions I have in the system? What about magnetic fields? Whenever you go to an astrophysical seminar, people will ask that. Is this important? Actually, turns out this is one of the most important ingredients. I'll show you some examples of this because it will critically determine when does the system collapse, when do you see an electromagnetic signal compared to the gravitational wave signal, and what is the property of the system as a whole. And then ultimately also dense matter neutrino effects are very important. So really all of these effects play in unison. We can use simulations to investigate them, put constraints, and hopefully nail them down by the time that we get the data coming in the high frequency band. Now, what I want to do is to sort of round off this topic is to say, well, what actually would it look like if a neutron star merger was a full collider? So I'm going to show you the movie again from the beginning, but this time I'm not focusing on the low density matter. So I'm not focusing on what we'll show you in a second will produce electromagnetic transients. I'm only focusing on what happens inside the star. I'm only focusing on the conditions that you would see in a collider experiment. So same movie. This time we put in a nuclear physics description that allows for deconfinement of quarks. So you take your neutrons and protons, you break them apart, and then we can see exactly what happens. So as we cut this thing open, at the center, we're going to produce very high temperatures. On the left, I'm showing the quark fraction. So watch out for our three-eyed friend over here. So you get small fractions of strange quarks appearing, about 10 to the minus 4 to 10 to the minus 3 relative fractions. And then the system continues to spiral around. It's very, very hot, and the correlation where the quarks appear is strongly correlated with temperature. There's a crossover transition appearing. And ultimately, at the center, the entire star confines. Nature is not kind to us, and this model is not stable, and then we'll collapse and form a black hole. Meaning that those densities are there, we can potentially probe them, but they're only very short-lived. And this depends strongly on the nuclear model that you're employing. One thing we're pushing for as a community, I'm involved in some project. This is a large NSF-funded cyber infrastructure project called MUSES, is can we make this connection more direct? Can we actually use nuclear theory, compute many, many nuclear models, just as the one that I've shown you, but maybe like 100,000 of them, using fiducial nuclear physics input, provide them to both LIGO, to heavy ion collisions, as well as to numerical relativity simulators, to see, can we establish a clear link between observational data that we will have? This can either be gravitational waves, it can be observables from heavy ions in terms of decay rates, or can it be observables in terms of ENM? And can we systematically connect them to underlying nuclear physics parameters? So can we, at some point when we have more data, do a very clear connection between the two? We're almost at the alpha release stage. So I think later this month, there will be a first version available. And I think it will really revolutionize the community in terms of how we can make this connection, how we can get our simulations more fiducial, and will also be available to the LIGO community as well, working with people coupling this in directly. Another thing that you can ask in the system is like, how generic is the picture that I'm showing you? Is it always the case that you form hot and dense matter, or sometimes you just form a black hole straight? The answer here is it depends. It depends strongly on how massive the neutron stars are. It depends on what model for the underlying interaction of the strong force you use in the regime found in neutron star cores. And depending on this, you end up with different scenarios. It's really like a Shakespearean question. Do you just directly form a black hole, or do you get all of the nice things I was just showing you? And one thing that the community has answered, and this was actually, I think it came at the cost of, I think for the entire community, about 200 million for hours. It was really, really expensive. It's millions of dollars that have gone into this. But by now we can provide a fit formula saying if you see a certain gravitational wave event with those masses, you either form a black hole straight, or it lives at least for a short amount of time. And this is something I think that's interesting. There was one observation, GW 190425, the other observed binary neutron star system in gravitational waves, where actually these type of relations obtained by many groups now and also all consistent, which I think is really encouraging, allow us to say which channel did we go. This has strong implications for should you do a follow-up for electromagnetic signals. One thing I also want to highlight is we also get very good surf students coming in. This is actually the first one I worked with after starting here last summer. And you can really make progress on understanding what are the transport properties in the system, how does it correlate, and what can we learn from it. And now what I want to do is I want to shift gears for the second part of this talk and show you a little bit about if you don't just have gravitational waves, or maybe for some of these systems that merge, you may never see gravitational waves because either the detectors are online or maybe it's too far away. Can we use other channels that we have? And this is something really exciting. It goes by the name of the multi-messenger picture of neutron star mergers, neutron star black hole mergers, and related systems, where we can use astronomical observations to learn about their properties. And one of them is all of this debris that was flying out in the movie initially. There was all of this low density smoky stuff that was leaving the screen. This is very, very neutron rich. So what happens is ultimately it has to go back, form stable elements. In the process, you form unstable isotopes. Those radioactively decay. You release a lot of energy. This powers heat. And ultimately, this powers observable emission. This is actually a really cool thing because it also produces a lot of gold, about the mass of the Earth in gold for this event. But it's also cool, especially for this place, because we have all of the observers over in the astronomy department who can look at this. And Mansi did some groundbreaking work observing the first event. This is what it looks like. It's a little bit small maybe here on the screen, but you see there's the whole galaxy. There's this little dot in the infrared that popped up. And this is where all of this afterglow, all of this heat that was deposited after about 1 day diffused out, and you could then ultimately see it. And seeing those light curves and how fast it decayed put very strong constraints on how much mass was ejected, ultimately on what is complementary to when they merged, what are their properties, and we can really use this as another window into the system to learn about the rich physics that is going on. And one thing I can show you here is how this works, at least for part of the mass that gets ejected. This is a similar movie to before. This time we don't focus on the high density, we only focus on the low density, and we color code in red and green the mass elements that can actually escape. So you have this collision, all of the stuff is flying out. Actually, if you follow this for longer, there's a very strong mass ejection going on. About half the mass that remains in the disk that you form over here is going to be ejected on long time scales, and that's going to power this type of emission that we can see across the various bands. This is something really, really exciting, and we hope that if we see more of these events, we can actually learn more systematically of how everything works together. Now, another channel that exists that I'm very excited about recently, just because we've seen so many of them, is gamma ray bursts. This has to do with very highly relativistic emission being flung out from the merger site. We've actually seen many of them over the past 30 years or so. And the interesting thing is, can you actually do statistics with them? Can you learn something about what kind of conditions does this merger need to probe to power them? There was one, this is the first direct association of a neutron star merger with a gamma ray burst that was done. You see this about 2 seconds later. And the picture that you should have is you have this dense ejecta cloud. Somebody switches on the garden hose. A strong relativistic flow of matter comes out, breaks out of the debris environment, deposits a lot of energy, and this is what you see. This one was actually very peculiar because due to the low energetics, we likely viewed it off axis, but it's a really cool thing. And the questions that we're now asking is, there's a very large amount of data for these gamma ray bursts. Which one of those come from neutron star mergers? What does it tell us about the equation of state? Does it tell us about the population? And the other cool thing is even, it's not just gamma rays that you can see. Also over Greg Callanan's group has looked extensively into the radio emission that you get both from the jet as well as from the cocoon after you have the breakout. So really, this is one of the things where we have everything in-house coming from gravitational waves, near infrared optical, and also the radio, where we can study the holistic structure of the system. I think this is pretty exciting. Now, being a physicist, what is the kind of picture you should have? And this is a very nice toy model. I want to show you how this works in practice. Here you have this accretion disk that formed after the merger, where I said, if you put on more physics, actually something is going to happen. And this accretion disk, this black hole is very hungry. It's going to eat up part of this matter from the disk. And then it's going to power a very strong outflow that's flowing out here. As the matter is going out, you convert internal energy into kinetic energy. The material is accelerating. This is the Lorentz factor. Now you're already exceeding Lorentz factor 2. Ultimately, you're going to get something like a Lorentz factor of 100 at later times. And this is really how you can power these outflows. And one thing that you can see here is how the computational approach, this is a very sophisticated code tracking with adaptive resolution, the interaction of the jet boundary. You can actually use this to systematically probe what's happening and trying to correlate what are the properties of breakout with the properties of the engine, how long is the time delay, because that's something that you can observe. And so really the computational picture here helps a lot. And one thing that we're trying to clarify right now in this picture is actually what's the time delay between this? How long does it take for this jet to be launched? We said there's an observational constraint of 2 seconds, but does that mean you form the black hole and then 2 seconds later this happens? Or how long did that actually take? And for that, what we need to do is we need to systematically study the black hole's diet. In fact, yesterday we had in the astronomy colloquium a speaker who is a self-proclaimed black hole nutritionist, who basically told us that black holes usually either tend to overeat or undereat, depending what conditions they're in. We usually find this system is sort of well behaved. It eats just the right amount. Sometimes we would like it to eat a bit more because then things would be faster, but it's something that I think we can probe and systematically understand. One of the things we have been trying to investigate, because I've told you that magnetic fields are really, really crucial in powering this outflow and also governing the properties of the system, is trying to understand the role of the magnetic dynamo. For those of you who haven't heard about this, you can put a little thing on your bike that converts rotation of your wheels into electric energy. And the same thing is happening in stars, in accretion disks, and also in the merger itself. For example, here, what you can see is in the sun. The sun has an 11-year cycle, meaning there's some low activity. Then midway through, there's very high activity. And then this sort of reverses and it goes back to a more quiescent state. If you look at the polarity of the magnetic field, something is happening inside the star. The magnetic field orientation is flipping, and you can basically do the same thing for these accretion disks. And also, as I will tell you, for the neutron star merger remnant itself, you could show that the same process operating in the sun in some part will be active as well, and will drive this very beautiful butterfly type diagram. So whenever this changes color, just like the solar dynamo changing the polarity of the magnetic field in the disk. Okay, and we're using right now the power enabled by exascale computing to really investigate what are the properties of these ultra high resolution accretion flows onto black holes in the neutron star context to really understand when does this outflow being launched, what are its properties, what are the winds coming from the system, and so on. And I think this is really, really exciting. And one of the questions that we can ask here is more generically, do you always need a black hole for this? Like starting from Roger Blandford, who was here many, many years ago, you kind of understand that you can convert black hole rotational energy into part of the rotational energy of this outflow that's being launched. And so you might say, well, you always need a black hole to get strongly relativistic outflows. One thing that we're kind of settling on starting last year only in the community is actually this may not strictly be true. You have this hypermassive neutron star remnant that you form. It can do similar things to the sun. If it does that, in principle, it can also drive strong magnetically pressure-driven winds. They're called magnetic towers in the high-energy astro community, and those potentially could power short gamma ray bursts as well. And so based entirely by new simulations that have been recently realized, we made some progress on this. If you wonder, is this just a simulation thing? There also has been some observational evidence, although this is somewhat murky, but I showed to you anyway. People have looked into gamma ray bursts from the 90s. They're large catalogs where people have observed them. And they found in 2 of them that are very highly resolved in time, that some of them can have quasi-periodic oscillations. So basically you get the main burst and there's some periodic thing going on with a kilohertz periodicity. And kilohertz is the crucial number because if a gamma ray burst comes from a neutron star merger, then the characteristic frequency at which the neutron star wobbles is in the kilohertz regime. This is exactly also where your post-merger gravitational wave frequency is, several kilohertz. And then the question was, can you actually correlate them? Does that mean if you see them, there's a wobbling neutron star at the base? If so, can you learn about dense matter just by looking at gamma ray bursts? I'll actually show you in a little bit. The picture may be more murky, but I think the motivation is a good one, and we should utilize this. So in part enabled by this, as well as progress in simulations, the community as a whole, several groups independently found out that yes, neutron star merger remnants can do this. If you look at these simulations here, for example, by Luciano Combi, Daniel Siegel, or this one by Kenta Kiuchi, is the highest one ever to be performed. If you have your own supercomputer, you run it for more than a year, this is what you get. It shows a very nice solar type dynamo being active in the outer layers of the star. We did a bit of our own work, actually guessing that this is exactly what should be happening. So we put kind of this effect in by hand before they figured out that it should be it. And you could show that this enables the star to launch this outflow, to get very high Lorentz factor, and to ultimately power both observational features in the afterglow as well as relativistic outflows themselves. And so really the dynamo problem, the magnetic fields in this case are really strongly important. It's something where we need both inputs from physics, astrophysics, and numerical advances. So I want to show you in principle what the picture is that was uncovered last year. So what is the main thing that we were missing out on? And this has really to do with solar activity. So how does this repolarization change in the sun? And so one thing that those systems have in common is they don't rotate at the same rate. It's not a rigid rotator. Rather, for this system, the interior rotates a bit slower, the exterior rotates a bit faster, and then you get a Keplerian envelope. This is where your disk is, roughly. But really the important thing is that they don't spin at the same rate. So the core is rotating a bit slower than the outer parts. Then if you have this dynamo being active, what it will do is it will generate magnetic field lines that buoyantly bubble up, go out of the star, and then get attached to different foot points here in this differential rotating background. This is kind of the cartoonish picture you should have. It's exactly the same. If you want to see what does that look like in nature, you look at the sun, you do an observation of these solar loops, solar coronal loops that are sticking out. They also have shear motion at their foot points. What will then happen is if you let this go, the loop will inflate, it will get bigger and bigger, and ultimately it will get ejected, just like you see in a coronal mass ejection or solar flare event in the sun. And the thing that we can show is because the dynamo is active, because the same phenomenon happens in a neutron star merger, the same phenomenology happens. You get periodic kinds of outbursts. Ultimately, this will collimate into this jet-like structure, and then you get a strongly magnetic pressure-powered wind from the system, which is really, really novel. And here computation really helped us understand what is happening. The same thing, by the way, also happens if you think in terms of a very nice observation done here for the galactic magnetar, which showed FRB activity. So there's a very interesting phenomenon of millisecond radio bursts that people saw extragalactically. And now they've seen for one known magnetar, so neutron star with extremely strong magnetic field, just as the one formed in the merger, that you see this type of activity. One of the leading models for this is that you get similar types of outbursts. We simulated them too and tried to make connections there as well. And so the overall arching structure that you should get from this theme is if you can systematically combine the all available observational channels with the underlying nuclear physics theory, both in gravitation or nuclear physics or plasma physics, neutrino physics, you name it, you can really use simulation as a connecting tool. And so the predictive power that we have both in interpreting these observations as well as in predicting them, I think is really, really nice and will enable, I think, future breakthroughs that we can do. Now, what I want to do now is, rather than telling you about the why and what we study it, I want to tell you about the how we study it. I think this is especially interesting for more junior people in the audience. It's like, how do you actually do this? And so if you do these type of simulations, I could now throw a lot of equations at you. I could throw a lot of math at you, a lot of computer science, but that's not what I will do. What I will do is I will say, well, making these little images is really just like painting them. So if you think in terms of this artist who's kind of painting her vision of what is happening, her view of the system, for example, here, this gamma ray burst that is coming out in her kind of painting style, you can make multiple of these images to highlight different features. And really, this is what simulations do. You focus on a particular aspect, you fix your painting style, you fix the colors that you use, and then you make these pretty images and you try to interpret them and connect them to real world observations. And so what I want to show you is, okay, how do we do this? How do we pick one? Well, here's how it works. So basically, if you think in terms of rather equations, you translate equations into different versions that I can copy from this image here on the right. So this would be the reality that you want to model. This could be some nice California valley. You have a stream here. You have some mountains. You have bigger mountains in the background, people dancing over here in the foreground. Okay. What is it what the computer actually does? What is it what these simulations do? Well, these simulations at different amounts of cost, different amounts of fidelity, make a copy of reality. You paint your own version. For example, if you want to go really cheapskate, you want to do a quick pencil drawing, you only include what I call hydrodynamics. Well, this is the version of reality that you get. It's pretty gray, it's pretty desolate. Maybe this is not what you want to use to connect today. If you include magnetic fields, which is this one over here, you at least see trees, you see people dancing, you see that there's a stream in the foreground, but there's no color. And no color basically means we lose all information. If you think in terms of what actually causes the physical emission that you see, the light that you see, this is what these simulations cannot model. We cannot tell you what actually your synchrotron emission from this process would be, what your electrons do, because they're not included. If you do something else, if you just adopt this brutalistic kind of approach, you get a little bit of color, but it's false color. So there's a different set of equations. So each of these things is a set of equations that you can pick. Typically, we're in this one because quick and easy is cheaper computationally, or you adopt something that is really, really close to reality, but there are corners you have to cut. So if you want all the color, you can see that your scales are all off. You see the people dancing in the foreground are as big as the mountains in the background. So you have to make specific assumptions. Those translate to the amount of physical fidelity you put, to the equations that you solve. You have to pick whatever is appropriate for your system, and then you choose what you like and what aspects you want to focus on. This is what basically the work is that most of us do. And then the interesting question you can ask is, beyond picking these things, how well can the computer actually do it? For this, you have very brilliant grad students who are working on, so even asking the question, if you tell the computer, this is my drawing style, can actually do it, or is there some intrinsic error that pops about? So Sarah has been looking into how do you actually make those kind of models more realistic, or how much error do they intrinsically cover? Then what you can do is you can apply this to different kinds of system. You can apply this to magnetar flares. This is if you want to study FRBs. You can apply this to jet type emission if you want to study GRBs. You can even, if you wanted to ask, well, how can I model low luminosity accretion flows? For example, this image that actually shows the gas dynamics around M87 and Sagittarius A star, where you can really ask sort of how do those flows work? And depending on what emission picture you take, you get a different answer. And there are some really challenges, I think, that we have to tackle, and how we make our numerical modeling more fiducial, how we can make better predictions for this. One thing I also want to say is, if your true passion lies at modeling black holes, this is nothing that you have to concern yourself with. What you actually have to think about, because there, if you say Einstein is right, there's no approximations to physics that needs to be done. But what you have to do is you have to pick a very different drawing style. This is what this looks like. You have to pick very, very accurate numerical models in terms of spectral models that you make that gives you this really crisp images of gravitational waves and spiraling black holes. And the question you can ask is, are they so complementary, or can you maybe do both? And one thing that another grad student here did is actually combine the two. So can I have color and can I have very accurate drawing methods? And the answer is yes. If you, for example, want to model this neutron star magnetosphere, this is an isolated neutron star. Here you see magnetic field lines. This is very important if you want to model any magnetospheric activity, in particular for radio observations. Can you actually combine them, that part of your domain uses these very accurate and cheaper methods compared to painting on some color scheme and then really giving you some idea of what the emission properties potentially could be. And so there are various combinations you can pick depending on what you do. This is really depends also on the prediction that you can ultimately make. Okay, we have a large variety of things available. Now, what I want to show you next is I want to really ask the question, does this actually matter? Could we not just, pick the cheapest one, run this, make a prediction, and that's just it? And I want to show you one very classical example that was, I think, first investigated also here by Kip Thorne many, many years ago. And this is a question of what happens when a neutron star collapses into a black hole. So the same thing that you saw in the simulation, with the difference is we just take an isolated neutron star and we ask, if it's too massive, at some point it forms a black hole, what happens? In the pure case where we are in vacuum, this is very well understood. If you add in magnetic fields, this is quite a challenge. And this scenario is actually not as toy problem as you may think. This is very applicable to the neutron star merger context as well, because if you wait, we have a system that lives for about half a day to a day, and Vikram over in astronomy a long time ago made a nice prediction that maybe lifetime can be up to a day after merger. Those systems will really look like this: isolated star, very strong magnetic field, you form the black hole, something has to happen. Because black holes cannot support magnetic fields, just like me losing my hair, they also have to bolt. When you shed all of this energy available in the magnetosphere, you can potentially power very strong transients that hopefully you can then later on see. And this is a very old problem that has been studied many, many times over. But the thing that we found out was, if you make the wrong assumptions in how you paint this picture, you infer the wrong answer. It's quite remarkable. And so what I will do is I'll give you two answers to pick from. So if the neutron star collapses to a black hole, and you use numerical relativity, you use this very sort of brutalistic drawing style, the answer you get looks like this. You see something that looks like textbook, like dipole radiation, just propagates out, and you would say, well, maybe there's some curvature emission going on, or maybe the shocks with something of the ambient medium. So should I ask my radio observer colleagues, go and look for this? Or option two, if you talk to high energy plasma physicists, what they will tell you is, no, this picture is all wrong. You should put the approximation where, you put all the color in, but you get all the scales right. So rather than simulating the far scales from the black hole is roughly here, you simulate only what happens close to the black hole. The dynamics looks very different. There's still blobs that emerge, and if the blobs collide, you get X-ray, which means that you'd have to talk to another observer in our department asking, how do I observe X-ray? And so the question is, what would you do? To which colleague would I go? Would I go to Greg and Vikram? Would I go to Fiona asking about X-ray? What would you pick? Who's for radio? Nobody. Okay. Who's for X-ray? Okay, some people are for X-ray. It's a trick question because we found out none is wrong. So what actually happens is, if you correlate this, and if you look at recent observations of both gamma ray bursts, as well as some claimed associations of fast radio bursts with gravitational wave events, I think both of them have quite heavy challenges, especially the right one here. I don't think that gravitational wave event, as it has been seen, is associated with the radio burst. But if you take it as a motivation, then the question is really, okay, maybe there's more going on. Maybe gamma rays should not be completely excluded. And the answer is actually, from a physics point, that's totally right. So the right answer would be, it should be gamma rays. And the reason for this is, as you get the magnetosphere being shed, as you get these waves propagating out, something interesting with them will happen. And you can see the same phenomenon if you go to the seaside, if you see waves that come ashore. So as these radio waves propagate out on the background, it's not just that they can propagate out unperturbed, because the background has a radial dependence. These waves will steepen, 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 much like this water wave that will come ashore. At some point, the wave steepens so much that it will break. At the point where it will break, it will deposit all of its energy. And if you start with enormous amounts of energy from magnetic dynamo, you also dissipate enormous amounts of energy. If you do this, you can produce a very bright gamma ray transient. We actually recently uncovered that there's a new model that can exactly produce this sort of phenomenology. So if you run the simulation, you put the right approximation, the right physics, so numerical activity, right drawing style, right picture, you actually see that these waves steepen into shocks. This you can see here in terms of Lorentz factor as well as temperature, that these very small regions that get very hot, very, very fast, they propagate out. They show exactly the same phenomena as the ocean wave. They will produce gamma rays, and they will power very bright, non-collimated gamma ray burst. Looks very different than the one from a jet, but with energies as bright or even more than the one you would normally expect. With the difference is it would happen one day later. It's quite a unique thing, and the physics is entirely rock solid because we get it all right. It's a really, really cool thing that simulations are now fiducial and crisp enough to capture all of those things. And another thing I want to answer, or at least partially try to address, is if you do really get the physics right, can we also say something about these quasi-periodic oscillations that people may or may not have seen in gamma ray bursts? And when you actually look very close at the simulation, what happens after the main burst has propagated out, black holes have a very interesting property. I think that was first found by Sterl as a grad student. If you have an oscillating black hole, what it will do is it will inject and ring down according to the properties of the space-time, according to mass and spin in Einstein's theory of relativity. If you assume that there would be corrections to that, the numbers would be different. And what we see is that at the collapse, the black hole is perturbed. It rings actually in the simulation exactly according to Sterl's equation, which is great. And you can see then that you get these periodic waves being ejected. They entirely depend on the properties of the space-time, which for neutron star merger is always kilohertz. And so the scenario itself has a built-in mechanism to produce kilohertz quasi-periodic oscillations. These waves can potentially steepen in exactly the same way. You suddenly get a gamma ray burst with quasi-periodic oscillations attached to it, from not neutron star matter, but from space-time itself. So really what we're saying here, much like the question, can you hear the shape of the drum? Maybe you could use gamma ray bursts, or some of them, to see the shape of space-time in this sense, which I think is a really nice finding that recently, together with collaborators, Columbia and CETA, that we found. And so, kind of motivated by this, I think the thing that's really crucial moving forward is to put more and more physics into these simulations, to make them more and more fiducial, to make really good predictions for what we expect to see, both in gravitational waves as well as in electromagnetic counterparts. Basically, where the field is right now is we're somewhere at the 50s. We have black and white TV, but really what we want is 4K Ultra HD. So we need to put more and more of the physics in, both from nuclear physics, plasma physics, maybe we want to do dark matter or modified theories of gravity as well, and try to make really good predictions for what's happening. And if you ask, how do you do this? Where do you take inspiration from? As I said initially, looking at how other fields did it for similar problems is, I think, exactly the way to go. So one thing that I usually do, because historically, I came from a place with lots of nuclear physics. I still talk to some of the nuclear physicists. Actually, here in the US, there are like very cool people working on how you can model these effects in heavy ion collisions, because those are known to not look like hydrodynamics. Those have actually corrections. If you're a plasma physicist, you would call them non-Maxwellian. If you're just used to typical hydrodynamics, you would say they have effective viscosity, but on steroids. So it's really, really complicated. And if you want to understand any of the emission physics, people who do spacecraft science, who try to understand, what happens here in the magnetosphere of Mercury, they really need very accurate predictions for what the spacecraft would see as it goes to this, it's called the reconnection region. How do magnetic energy, how is it that dissipated? Just like in the black hole case, what would that do? And so if you combine those kind of different formalisms, which mathematically has the form of an effective field theory, we're somewhere here doing hydrodynamics. What we want to do something that looks like kinetic theory, so more like particle dynamics. you can really, in a perturbative sense, try to correct the simulation systematically, putting in at every order sort of in between what we can already do, what we would like to do. For example, in this case, parameterize as part of the mean-free path. So if you kind of put some particles outside the box, they bounce around, you can systematically correct your simulation. And then ask the more and more physics I can put in this way, the more and more predictive I can be. Things that we've done, just to highlight a few of them, is how do you do relativistic viscosity? It's a very challenging issue because causality hits at you very, very fast. For those who are here for the colloquium of George and Ronja, I talked in depth about how the nuclear physics community dealt with this issue. And so what we're able to do is we're able to solve this in the astrophysical context. Things we're working on right now is turbulence in the relativistic regime. We're doing the first one actually that can match what you can do in the Newtonian case, have full viscosity, full heat conduction, all the nice properties that you have to really understand how those systems work. This has strong implications for the turbulent dynamo in the neutron star merger and in other systems. Things we're working on with new grad students is also, if you take something more exotic like a superfluid, not just like helium, but more like superfluid neutrons that you find in neutron stars, can we simulate that as well? Turns out the equations existed, but nobody had solved them. We tried it, we figured out there's a reason people have not tried to solve them, but we succeeded, or better say Yuan succeeded in doing this. And we can basically now simulate on the computer little superfluid vortices under certain assumptions that we can make, which I think is a really cool application of this technology. Other things that you can do in this form, you can try to augment your dynamo physics. As I said, this is really, really important if you want to make any connections to those electromagnetic counterparts to understand what is your magnetic field doing. This is something where I think more understanding from the theory side as well as from the astrophysics side has to be done. And we develop tools to include them also perturbatively, especially where we cannot afford to run for like hundreds of millions of core hours for every simulation, rather where we understand what the effect should be and we can manually put it in and make our simulations more realistic. And we even know, and this is, I think, something I'm really excited about going forward, how to do proper reconnection physics. This may help understand what's going on in this EHT image, how actually does energy close to the black hole get dissipated, what happens when these waves propagate out, what kind of emission process do they give, and this is really cool. It actually turns out going from order epsilon to epsilon squared is significantly harder than just adding one epsilon. So this is something where we have to do more work also on the numerics. Before I conclude, in the last 5 minutes, I want to give you one more example of how you can actually apply this to a problem that is both, I think, very Caltech and I think also very cool. And this is how can you make a prediction in this picture that so far has not been observed. And one thing that I told you is neutron stars have these built-in walkie-talkies. They have this potential radio emission, but if the magnetic fields before the collision, there's also there, they already interact in principle, just like in the isolated pulsar case. You could get emission from that as well. And that may give you ideas of what is the initial neutron star magnetic field. It may help you localize them. It may also help you tell what are the neutron star spins, something that you cannot easily constrain right now from gravitational wave data. So the question is, what kind of things should our observer colleagues be looking for there? What is the thing that you expect? Actually, they've already tried to do this. There was a proof of principle search for GW 170104. It's actually a black hole binary, so you don't expect much to happen, but you can at least check if the entire pipeline works. This was done at the Owens Valley Long Wavelength Array in Greg Callinan's group. And the interesting question there is, should the search be done with this instrument? This is something that would happen in a megahertz band, just as you know, as your receiver in the car, you have to tune what the frequency range is, at least in the older ones. What kind of instrument should they be using? There's a new instrument that hopefully will be built soon. This is DSA 2000, which will be operating in the gigahertz band. Is this a better thing to look at, just like where these fast radio burst events are? And the answer is we can actually use simulations to get some idea for what's going on. And so just as a very brief sort of overview of things people have been thinking there, this is just the type of different channels or models or cartoons people have drawn. It can in part be either come from X-ray emission. This would require an X-ray telescope. Some people, I will talk about this a little bit, have thought about gamma rays in this context. People have also thought about merger type, collapse type transients. So if a neutron star, as I showed you, collapses into a black hole, can actually do radio. As I told you, that's probably not true. It will probably rather give you gamma rays. Or can there be an interaction of the two stars? And one of the nice things, I think, what the community as a whole has done is to increase the fidelity of what these things actually should look like, going from simple drawings that you may do with pen and paper theory to actual simulation-based pictures of what should be happening, quantitative estimates, how much energy gets dissipated, and what exactly would you expect to happen. For example, here you see these flaring type outbursts that might be relevant for the galactic magnetar, as well as alpha waves. being launched that become nonlinear. It's actually a model that was first proposed here in 1989, as Sterl pointed out to me, by Roger Blandford, grad student and collaborators. And similarly, also the fidelity of these interactions. And one cool thing that we find that I want to highlight, if you actually come visit me in my office, this is what you find at the door, is the first simulation that actually reveals what the potential mechanism could be, what the potential emission that you would see from this process would be. And so what these things tend to do, if you get all the hair that's tangled up, they try to just like eject bundles of hair periodically with the time scale of the orbit. This is kind of this this like bluish thing over here. As this interacts with the wind from the system, there's a very well-defined emission mechanism that has been put forward for fast radio bursts. If you plug in the numbers for the system, you end up with emission somewhere above the gigahertz range. It depends very strongly in how strong the magnetic fields are. I think for fiducial numbers of 10 to the 11 Gauss, you get 10 to 20 gigahertz. If you're slightly below this, you can go actually to the range of what DSA 2000 can see. And I think it's a nice application to show you can use these tools in multiple contexts, make predictions, and then hope that people can observe them. And finally, I want to conclude this by showing you how you can apply them to something that I call the tapered challenge, a problem I think that has been around at tapered for at least 30 years. And the question here in the context of what we're thinking about goes back to gamma ray burst precursors. So not just that you could see radio before two stars collide, but it could also be that you could see gamma rays before that happens. And so people about 10 years ago started looking in gamma ray burst data for little tiny blobs and events that happened about 1 second to 100 seconds before the main burst occurred. Okay, if this was caused by a neutron star merger, and you think the main burst comes a few seconds afterwards, just as for GW 170817, then what this is saying is maybe a few seconds before, 100 seconds before, there must be some interaction going. And there's a model that has been put forward by former postdocs at Tapier. In fact, this poster, which is still there, is more than 10 years old of the picture that they put forward. Maybe either we like it so much or we just don't do posters anymore. I don't know. But definitely what you can do then is you can ask, okay, it goes with resonant shattering of the neutron star crust, which goes also by this earlier paper by Blaise, Blandford, and Goldreich, done many years ago for single stars. And so what's actually their model? I'll show you. This is the model that they put. There is the neutron star acting as a Valkyr, sort of just giving via tidal forces a very high-pitched, strongly correlated interaction. The shatters, think of a neutron star here as being more like a hard-boiled egg with a shell. You shatter the shell, and then some nuclear physics constraint pops out. Because the interesting thing about this is actually that the outer parts of the neutron star probe a very different regime in densities. It's not nuclear densities, so it's much far less energy than what you have in a nuclear collision. But it could give you complementary constraints about what's going on in this part of this so-called neutron star crust regime. It's actually something that I know Katarina and her PhD student Isaac are thinking very hard. And so the question is, if this is actually very interesting, can you use these observations, combine them with simulations, and really ask, how would that look like? What would be a more realistic picture than this cartoon be? Right. And the nice thing about it is this problem combines all the themes that we had in this talk. It combines relativity, this things orbit around, it's tidal interaction from the gravitational field. So you need gravity, you need nuclear physics because that tells you when the hard-boiled egg is cracking. And finally, you also need plasma physics because what the picture is lacking is what would you actually see? Is this really going to give you a gamma ray burst? Is it not going to give you something else? And the nice thing that we can do now with all the advances done on the physics and on the computational side is show you what the thing actually looks like. And this is what it does. This is showing you a neutron star black hole merger. This is work done together with Katarina, Isaac, and Yunsu, who's in the audience as a grad student at Tapier, where the idea is this is sort of your background. This is your neutron star. This is your black hole. There's a lot of magnetic hair that's being connected. And now what you do is you get sort of that this hard-boiled shell of the neutron star cracks. This is something that we do by hand because we don't understand the nuclear physics there fully yet. But anyway, you can kind of inject this manually. You can crack the neutron star. And what you see is that this wave here is propagating out. This is ultimately the wave that this picture had in mind. Once it cracks, it is going out. And this could ultimately, due to interactions with the medium, cause an observable transit. But the nice thing is we can do an ab initio simulation for exactly what the dynamics would look like. And there's some interesting features that we find. For example, the main wave here ultimately can give you shock-powered emission. It's something that Naveen and the audience has looked into, how you could correlate this with properties of the star, at which distance does it shock. Usually this is thought to give you radio if your magnetic field is not too strong. There's a second thing that we see. This is actually pretty cool. You see the same thing that the black hole was doing. They're these little kind of densities, and this is what is called a current sheet. Very likely this will give you X-ray emission. So we have X-ray yet, we have the shock power transient, we'll probably give you radio. We don't have gamma rays yet, but we're working on it. And the cool thing in this picture is actually making this picture is much harder than it may look like at this point. In fact, this required, you could think you could have done this like 10 years ago. The answer is you couldn't. This has required enormous amounts of computational power to compute. So if you actually paint a number, if you want to have one, this simulation was run on the equivalent power of 250,000 compute cores. If this doesn't tell you much, this thing has about 6 compute cores. When I went to grad school, the largest supercomputer in Europe had less than this. Okay, so just in about 7 years, the computational power has so ginormously increased that we can now run this, and the runtime of the simulation is a mere hour. So we can even use massive amounts of computational time, make novel predictions, and then really kind of study things we couldn't do before. I think there's a lot of opportunity there to be leveraged. Ultimately, what I want to say to conclude is, if you have any questions, stick around, you can ask me. You can also talk to the students. Some of our work I've already shown. People also work on things like dark matter, things like dynamo, many different things. If you have questions, talk to them, talk to me. You can find all of us in tape here. And with that, I'm happy to take any questions.
Okay, so I guess time will tell whether this was Dolly or Da Vinci that we were looking at. And, yeah, so questions.
Most of these images are actually AI generated. So I can already tell you where they come from.
Elias, earlier in your talk, you mentioned these like shallow water approximations on neutron stars. And I was curious, with gas giants, you see these polygon structures emerge near the poles. And I was curious, do you see these in neutron stars as well?
So what exact structures are you referring to?
So on Saturn and Jupiter, you have these polygons.
Oh, these ones, yes. The polygons we haven't seen. The challenge for this initial image is it depends very strongly on rotation. So actually what happens is you basically get, in terms of turbulence, you get a 2D cascade. So your kind of structures want to grow to larger and larger scale. And here in this particular image, we look at the millisecond pulsar. This is rotationally inhibited. This is why you get the little hurricanes at the pole. If you actually go to structures with very low rotation, then you would get large and large blobs. We've done that too on the side. And they might look closer to what you have in mind. It's a very rotation dependent.
So earlier you mentioned that quasi periodic oscillations may not be a very clear cut way to distinguish between hypermassive.
That's right. That's right.
Black holes.
That's right. So the reason for this is actually interesting. So the motivation for doing this dynamo work in terms of outbreak was actually to exactly see if the periodicity that you get in this relativistic outflow is correlated with oscillations at this stuff. Because even if you don't understand what exactly causes the actual emission mechanism of the GRB at large distances, if you inject periodicity already at the source, there's a way of potentially connecting this. And what you can do is, or what we did in this work, I don't have it on the slide, we actually correlated the gravitational wave frequency spectrum with the spectrum of periodicity in this outflow. If you do this for the model that exactly matches the data, you get a perfect agreement on everything. So you might think, oh, perfect, it's exactly this. If you change the model, if you pick the nuclear physics model that's close but different, you actually get no correlation anymore, completely goes away. And so the picture, I think, is very murky. I think there will be potential ways in which this will line up, but there will be many ways in which it won't. So this is why I'm more cautious in saying this is generically true.
So are there any other observation measures that one might expect to distinguish?
I mean, the main difference, and this is the main challenge for why you might need this jet-like outflow in the first place, is the amount of blue kilonova. So you get different kinds of colors, say, depending on how many protons you have versus neutrons. And the difference, if you have the star, you have a very hot irradiating surface, so you can get a very proton-rich outflow. And it seems that this may be needed to explain some of the expected morphology. So if you actually see that there's a change in the spectrum, which for 17 you actually see this. There seems to be an early time outflow and a late time outflow. That would indicate that you had a star and then it went away. So you can look for those type of features too.
Thank you, Elias, again.
Right.
But you were saying that the flat super neutrons are magnetized neutrons are a black hole.
Yeah.
See evidence for the quasi-periodic
Yes, that's right,
oscillation.
that's right.
But unless the black hole is near maximal, those have very little.
The only person in the audience, I think, planned.
10 oscillations where it's damn.
No, so it depends, as you say, it depends very strongly with the rotation rate. I mean, the nice thing is if you expect that this happens in the merger scenario, right? Then you basically collapse a star that's very close to the Clarion limit. That means that this feature will be very pronounced. If you do the same, and we did for very low rotation, it will essentially go away. Yeah.
So somehow you're saying it's very near maximum.
Exactly, because it's inspired by the merger remnant conditions. I mean, that might be one of the few conditions where you
But I guess that one,
can form.
I guess you only was really get maximal if you have, if you form a disk and then free. Right, because
That's
otherwise
actually-
you eject so much material and sort of leave.
Actually, no. This is what I looked into with the SURF student. We tried to understand. There's a very nice paper by Ben Margalis, Elliot Potter, and Brian Metzger, on trying to understand what exactly causes angular momentum transport in like a simplified model. And you have both something like a Taylor-Stewart type transport in the star, which is something we're simulating right now. You have both a late time accretion star. I think this is what you mean. And you have also just the regular magnetic braking. And it turns out that the late time, this accretion induced part is very much suppressed. So most of the angular momentum transport actually happens early. What we don't know is, does it mean that the star still rotates very fast? At least the simulations seem to indicate they actually spin up the inner part of the star. So you might actually end up with a very strongly rotating one. But yeah, we're looking into that.
Because the spin of the collapse of these things, because there's so much material ejected, maybe you have strong magnetic field. It seems very unobvious what the actual A over M is. Okay.
Yeah.
Thanks.
Thanks a lot for the nice introduction. Like I like the reference to Thomas.
Well, it was sort of nice. It's 90, I guess 10 years from now, I'll have the 100th anniversary celebration. At least this was around 90s.
All right, see you.